Welcome to this presentation on electricity. Electricity is the study of how charge moves and interacts. In this topic, we will look at current, voltage, resistance, circuits, and how electrical energy is transferred. Understanding electricity is essential because it explains how many everyday devices work. A-level electricity specification scope and assessment focus: electric charge, current and charge carriers, potential difference, and electrical energy transfer. The specification explicitly covers current electricity, current voltage characteristics, resistivity, direct current, DC, circuits, electrical power and energy, electromotive force, EMF, with internal resistance, and potential dividers. These areas are assessed across AS and A-level papers, with strong emphasis on mathematical application, graph interpretation, and experimental technique. Students are expected to confidently use defining equations such as I equals QT and V equals WQ, rearrange formulae, and apply proportional reasoning when analyzing relationships between variables. Electric current is defined as the rate of flow of electric charge, expressed mathematically as I equals QT. In metallic conductors, the charge carriers are delocalized electrons that drift through a fixed lattice of positive ions when a potential difference is applied. It is important to distinguish between the slow drift velocity of electrons and the rapid propagation of the electric field through the circuit, which explains why circuits respond almost instantaneously when switched on. Charge itself is a conserved quantity and is measured in coulombs, while current is measured in amperes. Potential difference, PD, is defined as the energy transferred per unit charge between 2 points in a circuit and is given by V equals WQ. This definition highlights that voltage is not a property of a single point, but of a pair of points, and it quantifies how much electrical energy is converted into other forms such as thermal, light, or kinetic energy. In exam questions, students must clearly link potential difference to energy considerations, for example when analyzing power dissipation in resistors or energy losses due to internal resistance. Resistance and Ohm's law in context, current voltage characteristics of components, resistivity and geometrical factors, temperature effects and superconductivity. Resistance is a measure of how strongly a component opposes the flow of electric current and is defined by R equals V or I. Ohm's law states that for an ohmic conductor, the current through the conductor is directly proportional to the potential difference across it, provided physical conditions such as temperature remain constant. AQA emphasizes that Ohm's law is not universal but a special case, and students must explicitly reference constant temperature in explanations. Microscopically, resistance in metals arises from collisions between conduction electrons and vibrating lattice ions, which convert electrical energy into thermal energy. Increasing temperature increases lattice vibrations, leading to more frequent collisions and higher resistance. For an ohmic conductor, the IV graph is a straight line through the origin, indicating constant resistance. A filament lamp, by contrast, shows a curve that becomes less steep at higher currents due to heating of the filament and the resulting increase in resistance. Semiconductor diodes exhibit highly nonlinear behavior. In forward bias, current increases rapidly only after a threshold voltage is reached, while in reverse bias, only a very small leakage current flows. Resistivity, ρ, is an intrinsic material property that quantifies how strongly a material opposes current flow, independent of its shape or size. It is defined by the equation ρ equals RAL, where R is resistance, A is cross-sectional area, and L is length. Low resistivity materials such as copper and aluminium are used in electrical wiring, while high resistivity materials are used in resistors and heating elements. Understanding resistivity allows meaningful comparison between materials and underpins required Practical 5, where students determine the resistivity of a wire by measuring its diameter with a micrometer and its resistance using an ammeter and voltmeter. Temperature has a significant effect on resistance. In metals, resistance increases with temperature because lattice ions vibrate more vigorously, increasing the frequency of electron collisions. Negative temperature coefficient, NTC, thermistors show the opposite behavior. Their resistance decreases as temperature rises due to an increase in charge carrier density within the semiconductor material. Thermistors are widely used as temperature sensors in control circuits and potential dividers. Superconductivity represents an extreme case, where certain materials exhibit zero resistivity below a critical temperature. This leads to no energy loss as heat and enables applications such as powerful electromagnets in MRI scanners and efficient power transmission. Series circuits and conservation principles, parallel circuits and current distribution, Kirchhoff's laws, and problem solving, cells in series and parallel. In series circuits, Components are connected end-to-end so that the same current flows through each component. The total resistance is the sum of the individual resistances, expressed as RT equals R1 plus R2 plus R3. This relationship follows from conservation of energy, as the total potential difference supplied by the source is shared between components. Parallel circuits provide multiple paths for charge flow, meaning the total current from the supply is shared between branches. The potential difference across each branch is the same, while the equivalent resistance is found using 1 RT equals 1 R1 plus 1 R2. This results in a total resistance that is always less than the smallest individual resistance. Kirchhoff's laws provide a systematic framework for analyzing complex DC circuits and are rooted in fundamental conservation principles. Kirchhoff's first law states that the sum of currents entering a junction equals the sum leaving it, reflecting conservation of charge. The second law states that the sum of amps around a closed loop equals the sum of potential drops, reflecting conservation of energy. The arrangement of cells in a circuit affects both the total EMF and the internal resistance of the supply. Cells connected in series increase the total EMF, making them suitable for applications requiring higher voltages. However, internal resistances also add, which can limit current at high loads. Identical cells in parallel maintain the same EMF as a single cell but reduce effective internal resistance, allowing greater current delivery. Electrical power and energy transfer, EMF, internal resistance, and terminal PD, potential dividers and sensor applications. Electrical power is the rate at which energy is transferred in a circuit and is given by P equals 4. By combining this with Ohm's law, alternative forms P equals I squared R and P equals V squared R can be derived. Electrical energy transferred is calculated using E equals PT or E equals IVT, linking power to time. Electromotive force, EMF, is defined as the energy supplied per unit charge by a source and is distinct from terminal potential difference. When current flows, some energy is dissipated inside the source due to internal resistance, leading to the relationship epsilon equals V plus IR. A potential divider consists of two or more resistors in series across a supply, producing an output voltage that depends on the ratio of resistances. The basic relationship Vout equals R2, R1 plus R2, VIN is derived from series circuit principles. Required practical, determination of resistivity, real-world applications of electricity, exam technique, common errors, and key equations. Required practical 5 involves determining the resistivity of a wire using measurements of length, diameter, current, and potential difference. Students must use a micrometer to measure diameter accurately, calculate cross-sectional area, and determine resistance from VI measurements. Electricity concepts underpin many modern technologies. Examples include the national grid, where high voltages are used to reduce power losses, thermistors in temperature control systems, potential divider circuits in automatic lighting, and superconducting magnets in MRI scanners. Linking theory to application demonstrates deeper understanding and is often rewarded in extended response questions. In this topic, we have explored charge, current, voltage, resistance, power, and circuit behavior. The key idea is that electrical energy is transferred when charge moves through components, and equations allow us to calculate how circuits work. Thank you for watching.